Mr. Calix here from Math Magicians, and we'll continue with our physics course. The answers, as always, of the last video. Today we're going to talk about vector operation, the theory part. Coordinate systems in 2 dimensions, what you see here. In the previous video of motion in 1 dimension, the motion of a gecko climbing a tree was described as motion along the y-axis. The direction of the displacement of the gecko was denoted by a positive or negative sign. The displacement of the gecko can now be described by an arrow pointing along the y-axis, as shown in the figure. A more versatile system for diagramming the motion of an object, however, employs vectors and the use of both the x and the y simultaneously axis. When we talk about simultaneously, it's used for phenomena that occur together at the same time. The addition of another axis helps describe motion in 2 dimensions and simplifies analysis of motion in 1 dimension. For example, 2 methods can be used to describe the motion of a jet moving at 300 meters per second to the northeast. In one approach, the coordinate system can be turned so that the plane is depicted. Depicted means that is represented by a drawing as moving along the y-axis, as shown in the figure A here. The jet's motion can also be depicted on a 2-dimensional coordinate system whose axes point north and east, as shown in the second figure here. There are no firm rules for applying coordinate systems to situations involving vectors, as long as you are consistent. The final answer will be the correct regardless of the system you choose. Perhaps your best choice for orienting axis is the approach that makes you solve the problem easiest for you. Let's continue now with determining resultant magnitude and direction. Earlier we found that magnitude and direction of a resultant graphically. However, this approach is time consuming and the accuracy of the answer depends on how carefully the diagram is drawn and measured. A simpler method uses the Pythagorean Theorem and the tangent functions. The use of the Pythagorean Theorem to find the magnitude of the resultant, you have your formula here. It says the length of the hypotenuse to the square is represented by c to the square is equal to the length of one leg, represented by a to the square, plus the length of a second leg, represented by b to the square. Let's continue with the next part of the video. Now, the use of the tangent function to find the directions of the resultant. For any right triangle, the tangent of an angle is defined as the ratio of the opposite and the adjacent legs with respect to the specified acute angle of a right triangle, as shown in the formula. Tangent of the angle, as you can see here, is equal to the opposite leg over the adjacent leg. You also have the inverse of a tangent function that states the angle is equal to tangent inverse is equal to opposite over adjacent. Now, resolving vectors into components, the next part. Now, resolving vectors into components. Components of vectors are shown as outlined open arrows. Components have arrowheads to indicate their direction. Components are scalars, that means that they are numbers, but they are sign numbers also. The direction is important to determine their sign in a coordinate system. Let's define a component of a vector. It's the projections of a vector along the axis of a coordinate system. In mathematics, the components of vectors are called projections. The x component is the projection of the x-axis, and the y component is the projection of the vector along the y-axis. Now continuing. You can often describe an object's motion more conveniently by breaking a single vector into 2 components or resolving the vector. Resolving a vector allows you to analyze the motion in each direction. Now, definition of a sine function. The sine and cosine functions are defined in terms of length of the sides of such right triangles. The sine of an angle is the ratio of the leg opposite the angle of the hypotenuse. It will be the formula that you see here. Sine of the angle, represented by sine of the angle, is equal to opposite leg over the hypotenuse leg. Then, the cosine of the angle is the ratio between the leg adjacent to the angle of the hypotenuse. The cosine of the angle is equal to the adjacent leg over the hypotenuse. Now, adding vectors that are not perpendicular. Until this point, the vector addition problems concern vectors that are perpendicular to one another. However, many objects move in one direction and then turn at an angle before continuing their motion. Because the original displacement vectors do not form a right triangle, you can only apply the tangent function of the Pythagorean theorem when adding the original two vectors. Determining the magnitude and the direction of a resultant can be achieved by resolving each displacement vector into its x and y components. Then the components along each axis can be added together. These sums will be the two perpendicular components of the resultant. The resultant's magnitude can then be found by using the Pythagorean theorem, and its directions can be found by using the inverse tangent function. All of this is the theory for vector operation. The next video would be the practice for vectors of operation. Thank you for watching, and don't forget, physics is life.